In this lesson, we want to be able to find geometric series that represent functions. So we start off with just a refresher of what a geometric series is. It has this form right here, and we know that that series converges only if the absolute value of r is less than 1. So we do have a condition for that convergence. And this is one of the special series where not only do we know that it converges, but we also know what a geometric sum converges to. So we know what that infinite sum adds up to if the absolute value of r is less than 1. So now we're going to be able to use that to write some functions, specifically functions that have this shape, rational functions, in forms of geometric series. So if we know that those two things are equal, what we're going to be doing in this lesson is we're going to be starting with functions that look like this, and we're going to be going backwards and writing those functions as a power series. So let's consider this rational function here, f of x is equal to 1 over 1 minus x, and it kind of has this form of what the series converges to, specifically when a is equal to 1 and when r is equal to x. So you can notice I'm just kind of matching r to x and a to 1 for that function f of x. So we should be able to represent this function f of x as a power series. If f of x is equal to 1 over 1 minus x, I'm now going to fill this part out and write it as a series, because we saw that a was equal to 1. So I'll put that there, but I don't necessarily need that. R is x, and the exponent on r is n. So this is really just the sum from n equals 0 to infinity of x to the n, which is in fact a power series. If I were to write out a few terms, when n is equal to 0, x to the 0 is 1. When n is 1, we just have x. When n is 2, we have x squared, so on and so forth. And it's equal to this. It's actually equal to this sum. It actually converges, but only if the absolute value of x is less than 1. Because remember, we know that generally speaking, geometric series will only converge if the absolute value of r is less than 1. And in this case, our r was x. So that general process that you saw of me taking this function and retrofitting it to match what that geometric sum converges to, and then filling out the a and the r in that geometric sum to get the power series, that's going to be happening a lot in this lesson. So we've represented this rational function as a power series. I do want to discuss briefly that we do have this condition here that the absolute value of x must be less than 1. So we can represent this function f of x as this series, the sum of n equal to 0 to infinity of x to the n, but that would only be true when x is between -1 and 1 because of the condition of convergence for that power series. When we know and have known from thinking back to pre-calculus, the domain of this function is all real numbers except for 1. We would take our denominator and set our denominator not equal to 0. So that function 1 over 1 minus x exists everywhere except for where x is 1 and has a vertical asymptote. But when we rewrite the function and represent it as a power series, we're talking about the function as this power series here, that power series only exists between -1 and 1 because of that condition for convergence. So we're saying they're equal, but they're only equal for certain x values because the power series only converges for certain x values. So this is the interval that we ended up with, the -1 to 1, when we centered our power series at 0. But let's look at what happens if we choose a different x value to center the power series at. What if it's centered at x is equal to -1? Now first, let's think about what does it mean to center a power series at x is equal to -1. That means that when we're finished writing that representation for that power series, there may be some coefficient here for the a sub n, but I definitely want to see an x plus 1 to the n inside of that power series. That's what it means for it to be centered at x is equal to -1, because it's x minus -1 raised to the nth power. That informs me that when I'm ready to rewrite this function as the form of a over 1 minus r, because remember that's how we start all of these. I try to match this up to a over 1 minus r, that I'm going to want my r to have the x plus 1 in it. So I'm going to set this up. I'm going to have 1 in the numerator. I'm not quite sure what's going to end up going there, but from subtracting this, I definitely want to have an x plus 1 right here. So the first point I'm trying to convey right now is simply because I'm now asking us to center the power series at x equal to -1. I know that x plus 1 to the n needs to show up in my final expression for the power series, which means that my r needs to be x plus 1, which means I need to have x plus 1 being subtracted from whatever number I'm going to be putting right here. So when I work that out, I can see this gives me a -x, this gives me a -1. I'm supposed to have a positive 1 in the bottom, and so this needs to be a 2. So now I have written this in a way that I can see where my r value will have the x plus 1. That's a little problematic for us because I need this number to be a 1 in order for it to match this form, the form of a geometric series and what it adds up to. So I'm going to have to come in and divide everything by 2. And you'll see us do this technique a lot, working with these power series, coming in and dividing everything by 2. Now f of x is equal to 1/2, 1, so I have the 1 that I need for the form of my geometric series, minus x plus 1 all divided by 2. Which is fine because I'm still seeing that x plus 1 showing up where the r is. So now let's go back and identify a being 1/2. R turned out to be x plus 1 divided by 2. So now I can fill this in to my power series, the sum from 0 to infinity of a, 1/2, r to the n. That's x plus 1 divided by 2, all raised to the nth power. And I do need to add in the condition that this sum only converges when the absolute value of r is less than 1, which does mean that the absolute value of x plus 1 must be less than 2. I'll quickly solve this inequality to get the interval of convergence. So notice now, when I centered this power series at -1, now I'm saying that this rational function is now equal to this new power series on this new interval from -3 to 1. So if you're trying to take a function and write it as a power series, and you'll see eventually why we turn these into power series, how this is helpful for us, depending on where we're going to use it. Sometimes we need to consider what x values do we want to be able to work with, and that may mean that we need to shift where we want to center our power series at. Values. In our first example, we're given a rational function, f of x is equal to 4 divided by x plus 2, and we want to find a power series representation centered at 0, and we also want to know when does that power series converge. I like to start off with the simple fact that we know that the sum from n equal to 0 to infinity of a r sub n, a geometric sum, converges to a over 1 minus r, given that the absolute value of r is less than 1. So the function that we have, we're trying to match the form to a divided by 1 minus r. So we can see, well, what is our a and what is our r? So we need 4 over x plus 2 to look like a over 1 minus r. Now, first thing I want to point out is the 1 in the denominator. That's very specific to the form. I need that number to be a 1 there. So the first thing I'm going to do with what we have, the 4 over x plus 2, is I'm just going to switch the order of the terms in the denominator and put the 2 first, because I know that I need a 1 to be first, and I can turn the 2 into a 1 by then coming in and dividing everything by 2. So I'm dividing the 4 by 2, I'm dividing the 2 by 2, and I'm dividing the x by 2. Now, I have, which I'm allowed to do after I've done it to every term in the fraction, I have 2 divided by 1 plus x over 2. Now that does look like a divided by 1 minus r, where we can see that, in fact, I'll take it a step further. If you want to see the minus sign, you need to observe that this is 2 divided by 1 minus negative x over 2. So now we can see that a is equal to 2 and that r is equal to negative x over 2. So we had to do a little bit of algebra first to get our rational function to match the form of the sum of a geometric series. To get from here to that form, to be able to see, well, what is our r and what is our x? Because now once we go from there to there, and we have, I said what is our r and what is our x, but I meant what is our a and what is our r. Because once we have our a and our r, I'm just going to be filling them in to what the power series is. So this is now equal to the sum. So I'm just following still from the function, because remember this function here, I'll just add in a line. These are all equal. The sum from n equals 0 to infinity of a, which is 2, r, which is negative x divided by 2, raised to the n power. And I'll write out a few terms of that sum, and we'll also talk about where that sum converges. So when n is equal, well, first things first, we have this coefficient of 2 in front of all the terms, so I'll just leave that there. When n is equal to 1, going back, when n is equal to 0, we get 1 for the first term. When n is equal to 1, we would have negative x over 2. When n is equal to 2, it would be squared, meaning it would be a positive term now. X squared, the denominator also gets squared to become 4. When n is 3, the term would be negative, because we would have to raise the negative 1 to the third power. X would be to the third power, and the 2 in the denominator would be to the third power, so on and so forth. And this never ends, so I'll just add a dot, dot, dot. And these are only equal to each other. Remember, geometric series only converge when the absolute value of r, which is negative x over 2, is less than 1. That is an inequality that we can solve. That goes back to 171, solving an absolute value inequality. Theoretically, we could just drop the minus sign. This is equivalent to saying that negative 1 is less than x over 2 is less than 1. Which means that x must be in between negative 2 and 2. That is our interval of convergence for this power series. So we have the power series representation along with the interval of convergence. I would also like to point out that we could have obtained this same infinite series by actually going through the long division of f of x, which was 4 divided by 2 plus x. If we set this up, we're seeing how many times does 2 plus x divide into 4. We're going to do this the same way we do polynomial long division. We start looking here and here. What do I multiply 2 by in order to get 4? I have to multiply by 2. I'm going to multiply the 2 by the 2 plus x, which gives me a 4 plus 2x. And then I come down here and I subtract. This becomes negative, that becomes negative. I now have a negative 2x. What do I multiply 2 by to get negative 2x? I multiply it by negative x. I'm now going to multiply negative x times 2 is negative 2x. Negative x times x is negative x squared. And then we subtract, so this becomes positive and that becomes positive. This cancels. I now have an x squared at the bottom. The process continues. What do we multiply 2 by to get x squared? Think about that for a second. What do you multiply 2 by to get x squared? Well, whatever I put inside these parentheses, I need to cancel out the 2. And I need to be getting an x squared in the top. So I multiply it by 1/2 x squared. And now multiply that 1/2 x squared by the 2 plus x on the outside, leaving me with x squared plus 1/2 x cubed. And then we subtract. This becomes negative. This becomes negative. These cancel. We now have a negative 1/2 x cubed down here. What do we multiply 2 by in order to get negative 1/2 x cubed? Well, I'm trying to get a negative 1/2, so I'm going to put a 4 in the bottom because 2 over 4 will give me the half. I'll also stick a negative in, and I'm going to need the x cubed. So I need a negative 1/4 x cubed on top. That is what I multiply 2 by to get negative 1/2 x cubed. And then I also multiply that negative 1/4 x cubed by the x over here to get a negative 1/4 x to the 4th. And then we subtract. So these signs change, and I'll stop the process here. This continues on, but I hope you do see that the quotient that we're building on top here is the same thing as this infinite sum that we got there. Mind you, you would need to distribute out this 2, this coefficient of 2 in front, to see those terms matching up exactly. So we can build a power series by using what we know about a geometric series, retrofitting the rational function to the convergent sum of a geometric series, determining what A and R are, and then substituting those expressions into the geometric sum. Alternatively, sometimes we can run through the long division and form the power series. Mind you, if you have this quotient, you should then be able to take that quotient, write it as, like, to work backwards, to be able to factor out the 2, write it as this expression, and then see what pattern is going on between those terms to write a general formula for that power series. In example 2, we again want to find a power series representation for a rational function. This rational function looks a little bit different, or actually a lot different really, because when we're retrofitting our rational functions to what the geometric sum converges to, it's very specific that the denominator down here should be linear, which is not the case that's going on in our function. We have a quadratic denominator, and so we're going to have to first decompose into partial fractions. So I'll set up my 2 undetermined coefficients. I will multiply through and clear out my denominators. And I will let x equal 4. It will give me 9 equals b. And then I will also let x equal 3. That will give me 7. Plugging 3 into this side equals negative a, which implies that a is equal to a positive 7. So now I know my function f of x can be represented as 7 divided by x minus 3 plus 9. A is a negative 7, so this is negative 7 divided by x minus 3, because negative 7 was equal to, when I plug in x equal to 3, I get 7 is equal to negative a. So a is equal to negative 7, because we have to multiply both sides by negative 1 to solve for a. So we have negative 7 over x minus 3, and then for b, we have 9 over x minus 4. So now we have decomposed that rational expression so that now we have 2 rational functions being added together, and they both have linear denominators. For the sake of convenience and what we saw in the first example, I am going to go ahead and move these denominators around to write the constant term first, because in order to retrofit these to a over 1 minus r. I'm trying to forcefully build that 1, which means that in that first rational expression, I'm going to have to go in and divide everything by -3. And in the second rational expression, I'm going to have to go in and divide everything by -4. So now I can see that the function f of x is equal to a positive 7 over 3 in the numerator divided by a 1 minus x over 3. And then the second term, we have a negative 9 over 4 divided by a 1 minus x over 4. And now we should be able to see what a is for the first sum and what r is for the first sum. Notice I don't have to change signs on r because I do truly have this 1 minus right here. And then in the second term, I can see that a is a negative 9/4 and that r is an x over 4. So I now should be able to write these two rational functions as two power series. One for this one would be a r to the n, r is x over 3 to the n power, and that's a sum from 0 to infinity. And then for the second rational function, we again have a sum from 0 to infinity. This time a is a negative 9/4. R is now x to the 4th, and this is raised to the nth power. The first sum only converges when the absolute value of r is less than 1. Similarly, the second sum only converges when the absolute value of r is less than 1. Solving both of those inequalities gives me an interval of convergence of -3 to 3 for the first sum and -4 to 4 for the second sum. Mind you that the sum of these two sums is only going to converge when they both converge. So if the first one only converges from -3 to 3, and if the second one only converges from -4 to 4, the overall interval of convergence needs to be from -3 to 3. Because the first sum is not going to converge outside of for x values larger than 3 or for x values smaller than -3, even if they don't go past 4 or -4. The last thing I'll do is I'll just clean this summation up a bit because I can pull out coefficients, which isn't necessary, but it's just making the final answer look a little bit nicer. But we do already have our power series representation for this function, and we also have its interval of convergence. Now we have another rational function for which we want to represent with a power series. Our first goal is always to represent the function f of x in the form a over 1. So if I'm trying to write this as 1 minus r in the denominator, ultimately I do know that I'm supposed to have a positive x in the denominator, and so I need to put a negative x inside the parentheses so that negative x will turn positive when the minus sign is distributed. And then I don't need this 1 because it didn't show up in this denominator, so I would need to cancel that out. So I'm going to put a positive 1 in here because then the minus sign will distribute to that and leave me with just a positive x in the bottom. Another way you could have done that is that these things have to be the same as what you're trying to match. So you need x to equal 1 minus r, and then you could just solve this equation for r. And if you solve for r, you would get that r is equal to 1 minus x, which is exactly what I have inside here, just written in a different order, and that doesn't matter, as long as you make sure you have your signs correct. Okay, so now we can see that a is equal to 1, and that r is equal to negative x plus 1, or 1 minus x. It doesn't matter which order we write it in. I'll write it as 1 minus. I'll leave it as negative x plus 1. It really doesn't matter. Let's fill out the sum now. So when I say fill out the sum, I mean specifically the geometric sum of a r to the n. These are all equal. A is 1, so I don't have to write that. And r is negative x plus 1 that gets raised to the nth power. I'm going to clean this sum up so it does look like it is centered at 1, because centered at 1 means that I want to be seeing powers of x minus 1 on the inside of the sum. But right now we have negative x plus 1, so inside of those parentheses I'm going to need to factor out a negative 1, which would turn the x positive and the 1 negative. So good, now I do have what we want, and I'll finally write this as what it is, which is an alternating series centered at 1. Note that this series only converges if the absolute value of r, which is 1 minus x, or negative x plus 1, is less than 1. So I am going to solve that inequality. Solution to this inequality would mean that negative x plus 1 has to be greater than negative 1 while also less than positive 1. I'll subtract 1 throughout this inequality to get negative 2 less than negative x less than 0. And then multiplying everything through by negative 1 gives me that the interval of convergence is from 0 to 2. So we have the interval of convergence for the power series representation of our rational function 1 over x. So again, to be clear, what this means is that if you're working with this function f of x, you can use this power series representation, but you can only use it on the interval from 0 to 2, for only x values between 0 and 2.